Good evening. Thank you for joining us. It's my pleasure to introduce tonight's speaker, Matthias Kohler. First, let me tell you a little bit about the formalities of who Matthias is, and then I'll tell you a little bit more about how we met. Matthias, of course, is an architect which operates in a very multidisciplinary way, together with his partner, Gramazio, his firm, Gramazio Kohler Architects. They have been in ATH for 20 years plus, doing a lot of research, fascinating work, intersection between physical and digital, robotics, materials, and everything in between. He's currently the Dean of the School of Architecture and the ATH. And we were talking early on, like many people here, trying to rethink where we go from here, how the digital is evolving, how things are start to operate, how we can keep connecting humanity with technology and all of that. He has been at the forefront of many of the most cutting-edge research and initiative in Zurich and ATH and through his firm. We met almost 20 years ago, 2006, walking around. This may sound fancy, but the circumstances were not. Walking around for a whole day in Paris. We were both, among with other young architects at the time, invited to be part of a competition in France for an art collector, Nathalie Seruzzi, and we spent a whole day commiserating, being sore losers because we both lost the competition. Somebody else won, which is gonna remain unknown for all of you. So we spent a whole day doing what architects do, criticizing the other architects and the winners of the competition that we don't win. So that creates a special kind of bond. There's nothing like the bond of losing together and finding common ground in that. The other thing which is very unique about Matthias is he has an incredible sense of humor for a Swiss. So this is something I always find remarkable over the years when we keep bumping into each other. But jokes aside, this has been one of those people that on and off you're in connection and you follow what the work is doing because there are commonalities and certain aspirations and ambitions that they have a lot in common of things that many of us do inside, but also it's very different. And it has to do with context, it has to do with culture, it has to do with the realities. The difference between the education and the research and investigation and practice in the European context is very different than the one in America. But there is a lot of these things, as I said, that they have in common. And their work is really a fantastic example about the notion, of, as I said, of precision and assembly, and rethink about how automation and the digital can interact with the tactile, the materiality, and the necessity of the reality of producing things, and of course, operate in all the scales. So it's truly a pleasure to have Matthias here tonight in Zurich. I'm very eager to see the work they have been doing over the years. Again, it's a very unique body of work. It's a work that it really sits in the intersection of research, practice, investigation, and innovation. And I think him and his partner represent among the most interesting people that have been doing that kind of work in the last 24 years. So please join me in welcome Matthias Kohler to Zurich.
Okay, from loser to loser, thank you very much for this very kind introduction. Amazing. So I would like to talk to you a little bit about this digital materiality in architecture. It's actually a title which is very old, from 2008, but it's still relevant for us. It's about the fusion of the digital and the physical in our realities, and particularly also in the material reality of architecture. I'm going to present work of our research group, Gramazio Kohler Research at ETH Zurich. The group is now in its 20th year. Together with Fabio Gramazio, we do research basically on the intersection of how humans and machines meet when they design, how that can manifest in the production of architecture, in the thinking of architecture, in the design of architecture. If we zoom a bit back, this is how we started at ETH. It was 2005 when we got this first robot, which you see here. And this was our technician at the time sitting on the robot for this photo picture by a photographer, Jules Binach. And it depicts a bit this ambiguity, this relationship between machines and humans. So who is actually controlling whom? And I think in today's time, also relating to questions about artificial intelligence, etc., the question still remains, right? Who is controlling whom? And of course, Mike, our technician, controls the robot, but in other ways, is the robot and automation actually controlling him? So these are questions which are not answered and are still lingering, but they were present from the beginning of our work. If we go a little bit further back, at the beginning of our office practice, actually 25 years ago, we already did projects which kind of brought these material and digital aspects together, like here with this first programmable mobile phone, where basically a few years before the iPhone was on the market, on this little Nokia cell phone, you could actually design a table with the pressing of a thumb. You could basically move the cursor and introduce holes into your table. You could select the colors and the size of the table parametrically. You could design it really on your fingertip. And with these little gestures, you would actually produce this code, which then basically signifies where you put holes onto your table and how much the force of your thumb was at that position. And then this would be regenerated, this information in a higher resolution on the server, and then this would be the production data for the milling of this table. And now where you pushed with your thumb, there was actually this physical imprint of the mill going down into the table surface and actually up to the point where it creates this hole. So where this one surface here actually meets the lower surface below. So this became the table with holes. It has these beautiful features of, you can see basically the milled side is on the underside, that you have this slim edge which appears. It has this very tactile underside of the table. If you sit at it, you actually touch it. You sense that this is different from the typical mass of the table. And it was this concept that people could co-design this table by using their mobile phone. Of course, we didn't produce so many of those. It wasn't mass-produced, mass-customized system that was a huge production success, but the fantasy was there. So people were using this software. Here's a couple of these designs that were made. And what was important for us as designers was saying, well, we designed this system which allowed other people to participate in the design of their individual tables. So basically we delegated the ultimate form of the design to the users of that software. But still we felt like we were designing this table. So we were designing these families of tables which could be co-present here on the computer screen or as a physical object. 7 or 8 of these tables got produced, and luckily enough, a few years later, actually the first table became part of the Vitra collection of the Vitra Design Museum. You see it here on the back left, the table with holes, the mTable. So this is how a little bit of parametric design history has been written in a small example. But it was very important experience for us because we learned that we could design with algorithms, with processes as conceptual part of our design intention, and at the same time create physical reality through it, which also was usable and had its own design features through the programming. Later, if we go forward, we did work which maybe most of you have known, but maybe I'm going to represent it because we're still old generations, or maybe newer generations don't know that work. Here was one of the earliest works which we did with the robots. So this is a building designed by Matthias Architects, and they invited us to design the facade. So this facade that you see is made from bricks, and this brick, and we designed this building in a way that we looked at the building as an empty volume, which we filled with these over-dimensioned spheres, representing grapes. Because this building was a building from a vineyard, from a wine producer. And so these spheres represented wine grapes for us, but as an abstraction. Then we looked at this virtual container from the different sides. So you see here this virtual volume. If this turns, you see that from all the sides, we now have a view into this filled basket. And then from each of these facade sides, we basically render the image of this virtual content to the facade, and we translate it into the rotation of the individual bricks. So each brick is slightly rotated. It's from -17 up to +17 degrees. It's a very slight manipulation, but this slight manipulation is enough to change the entire appearance of the facade. So it's a traditional straight brick bond, but with slight rotation of the individual brick. This is how it was produced. You see here we programmed a robot as part of our research to put these bricks on top of one another. Here you see how he puts the glue onto these individual bricks. The glue is put exactly at the rotational intersection of the new brick and the two underlying bricks. This is something which would be difficult to make by hand without spilling the glue all over the place. And here, in a way, we 3D printed this design, or additively manufactured this design out of bricks by use of the robot. And for the sake of time, I'm going to continue here. You see here in the inside, we also get a sense of these abstracted grapes in the counterlight. A very beautiful, also very functional facade. It allows the direct sunlight to be blocked out, but still has this diffuse light which is needed for the working space in which we are here. Then we took the robot to Venice, and this is probably where our work then got known. We actually packed it in this container, and we produced building elements, again out of brick, directly in front of the Swiss pavilion. In the Swiss pavilion, we built this 100-meter long brick wall, which was part of a collective exhibition. And we did it in a way that this line was actually a line which was drawing the different, or creating a zoning between the different exhibition areas within the pavilion. So like a new reading of the original pavilion. And the brick walls which we produced were actually an expression of this original design. So while this line could have been changed to any other shape at any moment up to the moment of production, there was an algorithm which created this oscillation of this line where wherever this wall, I cannot move, wherever this wall is straight, it would start to oscillate, and where it's curved, it would just stay as it is. This was as the reason that this line was produced by singular elements, and these singular elements all needed to stand by themselves without any further mechanical fixation to the ground. So this line needed to behave in a way where each production element would create self-standing elements. And this became the expression of this wall. You see here how it curves and undulates in ways where it's actually like a folded sheet of paper. You can just put it there and it stays and then you simply connect element after an element, and it creates this kind of actually quite elegant, and I would say, you know, selbstverständlich, what is it in English? Kind of natural appearance, which comes from the principles which are built into the design and production of this wall. A few years later, in 2016, we had the chance to actually be part of a collective design of our institute building. It's an institute where 9 professorships are hosted in, and we're one of the professorships, and we were responsible for the design and the fabrication of this roof. You see this roof here spans over 500 square meters of a hall. And you can see it is composed out of 50,000 individual slats. No slat in this roof is the same. You see these different coloring of the slats represents different dimension of the slats, which are structurally optimized in order to reduce the amount of wood and timber used in this roof. These slats are assembled in layers, and each layer is connected through nails. Overall, there is 1 million of nails in this roof. And of course, this is a task which you would never want to design and draw by hand. Imagine drawing such a roof by hand, drawing every slat, drawing every nail, ensuring that no nail hits the nail in the next layer. These are things which only make sense in a computational logic. You design them computationally, meaning you design them by programming it, and you build them robotically. Here you see the production of this roof. So it's actually just made from these very simple slats, which are cut at an angle. This machine from our industrial partner. And then, again, these slats are laid out in a kind of 3D printing process, but with discrete elements. Then slat by slat is assembled spatially or layered in a layered manner on top of one another. You see this aggregate is also doing the nailing at these positions. And these patterns are to code, but they're not regular. So they were computationally found, these nailing positions, but you wouldn't understand why which nail is where it is. It makes sense to the computer, it makes sense in the computer, but it's not of a human readable logic. Here are the elements. They span 14 meters. And they incorporate all different building elements, natural lighting, artificial lighting, sprinklers, etc. So it's all part of this composite roof, which kind of embeds the functionalities in its own thickness. Actually, it uses less timber than a traditional construction for this roof. I was also surprised of learning that, but that's actually the case. So by spatializing the material information and giving it the shape which it structurally wants to have, and giving it the architectural expression which we wanted it to give, we actually also saved timber. But then there is entire other categories for digital fabrication. There's more messy stuff than just discrete assemblies. Like, for example, if you build with foam. This is an early experiment which we did with polyurethane foam. Not the most healthy thing to do, actually, but for the time, that's what we did. And the interesting thing is here that you start to learn about the temporality of construction processes. Because here we have 2 temporalities which overlap. One is the robot with its movement process in time, and the other is the material formation, that polyurethane foam, which slowly starts to foam up and gain volume over time. these two temporalities start to overlap in this process and start to create a more complex morphology. So here the robot has terminated, and you see how slowly the pattern is transforming with time, and this is the final panel. You see how it features kind of intricate formal expressions, which are kind of the material computation which result from the temporal deposition of the material. We can see this very well in this panel as well. On the left, you see the geometric abstraction of what the robot was doing. So this was simply the path of the robot, with the beginning and the end marked on the left, lower left corner of the path. So that's why you see it is not just a grid drawing, but it is a path drawing. And right is the physical reality which it produces. And I think this offers this possibility to think of the materials as kind of actors, as producers in a digital fabrication process. So not only being the recipient of information, but also being kind of a material co-computation of sorts. We explored this further with students, for example, with sand deposition. This is a very simple process where you just open and close a valve. But if you look closely now on this mountain, which is just being deposited, you see a red dot. Did you see that? This red dot is a little sensor. So what the students did here is they programmed when to open the valve, and then they went back to that position and scanned how high did my mountain actually get. And their program was then a kind of a response to that development of the physical computation and the reaction to that. So here, the design is not so much a design of geometry, but it's a design of interaction with a material reality. Here, for example, a hand-shaped kind of landscape, which got then read by the sensor and then interpreted by the sand deposition developed by the students. What is very beautiful with these sand depositions is that you have an extreme resolution and precision, although the process, the manufacturing process is actually very, very simple, very banal, actually. So here you see, for example, what then the students tried to do. We put on a coat of latex onto this sand bed and used it as a mold for concrete panels. And then we got this very beautiful individually produced panels on a sand bed, which you could constantly reuse the sand and create other types of molds with. Going a bit further into this material exploration, we were more and more interested in very ecological processes. So how could we build in a way that ideally, you see that here on the left, we could assemble material in a structurally strong form, and then if we take away the force of the building, let's say the stories on top, then we could just regain the material which is part of the building. We explored this idea, which is a physical phenomenon called jamming, with this bulk material, so gravel you find everywhere on this planet in different qualities, but basically it's an abundant material which is available throughout. And then we did a lot of experiments. Okay, how could we stabilize such gravel compounds? On the left you see all the failures. On the right you see the successes of these early tests. So on top of this mechanism is some weight which pushes down, and we were interested in finding this moment of equilibrium where material which is not fused together by any binding material would actually be stable in a sort. You see here on Skylar Tibbets, he was working with us on this early phase of research. Here are then the success. You see this enormously slender configuration of stones, which with a little bit of string actually gain stability. What's actually happening here is that the string actually just holds back the stones such that they cannot move. So the string don't have a lot of force on them, but they just create enough confinement for the stones not being able to move and fall apart. This was super exciting. You get this material which is a bit fluffy, a bit soft, you know, a bit squishy, but it's made out of rocks, right? Rocks and string. So this was super exciting for us. Discover what could material do if you go towards it and figure out what you can do in the combination of these materials in order to build more ecologically. We were then invited to the Chicago Biennial and built this, this piece. This is an early prototype of it. And you see the design principle here is that you give it as slender as possible legs such that they are under a lot of compression, because the more compression the legs have, the more stable it is. If you disturb it, it falls apart and actually it liquefies, right? It's an architecture which liquefies if you take away the constraints and let it go. And then you have the raw material back. Here's now a video of how we then finally built the piece in Chicago. We used some lightweight gravel aggregates because the floor weight was limited in the gallery. And the robot basically laid out this pattern, layer by layer, kind of a 3D printing process with this string. And then by hand we put another layer of gravel. Very archaic process. And then we could open this box. This gravel now sticks a bit because it's this lightweight gravel. It was a bit more sticky than traditional gravel. Carefully open it. And now you could actually unearth kind of this form simply by gently scraping it. You have all the loose parts falling off. And you have the parts which are held back by the string, which remain stable under this weight. Then, of course, the most exciting thing, besides the fact that there is no structure inside of this, which always caused people to be quite stressed when they learned about it, particularly if you brush a bit on it and stones fall off, and you have this intricate expression, these details like these little stones hanging on the edge there. Was actually the most interesting part was then the build back of it, because what we could do is basically simply reverse the process. So here you see Petrus, our project lead, just basically pulling out the string in the reverse order of the fabrication process from the structure. So with this little performance, basically we gain back the raw materials of the installation. So we gain back the string on the spool, a bit more dirty than before, and the gravel, which we then donated for another project. Now, this was a beautiful experience. This collaboration with Skylar Tibbets worked really well. And then we wanted to push it slightly further and say, could we actually really build kind of a building-like structure with it in a public space. This was pushing the limits a bit for the time, but we actually realized it. Here is the structure. It's in a public space. It was there for 1 month. We actually got approval by an engineering office, but they were very scared on how to do this, because basically, the way that it was possible to do was by monitoring the roof daily in order to ensure that it wouldn't move. Because if this structure slowly starts moving, then you could actually foresee that it would collapse. But actually it didn't move at all over the time. There was a little bit of vandalism because some people started brushing the structure, and it's most vulnerable to these soft interactions. And then also the build back process. Basically we took off the roof, which was there in order to create the weight to stabilize the structure. We did the same thing. We pulled back the string. And we regained the raw materials. And for us, I'd like to show this project because for us this is probably the closest you can go to kind of basic research in architecture. It's basically saying, wouldn't we like to build like this? So bring materials to their shape and bring them back as resource for other configurations in a later construction time. So for us, this is kind of a sign on how to build in the future. It's not a construction method which is practical yet. So this is, in a way, early research. But it's still a nice prospect if you can just come and then you vacuum up the gravel like we do in Switzerland. And you can reuse the gravel on another side. Yeah. On these ecological methods, I mean, we like to play with materials. We love to do that because we learn so much when we do that. We did this project where we actually were shooting clay. We were interested in the question, or puzzled by the question, well, how could we build with robots without needing to bring robots always to where the material needs to be? So we were interested in the idea of shooting material to its location. And we did this in an art institution in Switzerland, the so-called Sitterwerk. So this was the raw material, and we portioned it in little clay bullets and kind of peacefully shot them to their destination. This was done in a simple ballistic move. You see that here. So this was the shooting mechanism, and the little robot that guided the shooting mechanism to the right location. And like this, we could build these wall structures, and you see again this very strong expressivity of this kind of particles that landed and the deformations they had while they landed. So there's an entire narrative on how this structure was made, which it becomes part of this structure. You can see that here. Here is how that looks from a landing position. You see it's coming. And here's the impact. But this was kind of 10 years ago, and then sometimes these processes, they linger with us. We say, we should continue working with this. And a bit later, a few years ago, we got this invitation to actually design a structure for a music studio. So this is a high-end music presentation room, which needed acoustical mass. So we said, let's go back to this clay. And basically, we took the principle of merging clay into one another, but we needed a much more controlled process. So we knew we couldn't shoot this structure because it would simply not work as a structure. So we did the exact opposite and basically started to just press these clay particles into one another and created this larger dome structure, which is only about 12 to 15 centimeter wide, but 5 meter high. It's actually quite a beautiful and very fragile structure, but or thin, elegant structure, but built from massive clay. You see here this piece. This was then taken on in research, and now we started to combine the earliest idea of shooting with this more controlled version. You see again the bullets on the right, but now it's a mechanism which kind of speeds them up to a high speed and is actually able. This is a bit sped up. It would be nice if it would be so fast. It's actually able to shoot these clay particles into one another in a way that they fully bond with one another. So it's an idea of kind of automating adobe construction, because we cannot build in clay anymore in Europe. I don't know how it is here, because it's too expensive. In our context, it's simply too expensive. So we try to find ways where we can say, what could we automate, and what kind of new expressive result would such a construction method give? In example of these kind of ecological construction methods, which involve digital design and digital fabrication, I would like to show you this project. So here we build with really large elements. On the left you see gneiss, so a Swiss natural stone. On the right you see concrete waste. Left stands for the natural materials which we have at our disposal, which we can extract, but of course the extraction is in some degree limited. Right is the new raw materials which we have, which is the waste from our urban production, from the deconstruction of our buildings. Now, if we take, this video is not playing. Now, basically, by taking a big walking excavator and giving it the sensor, it now can scan the stone which it holds and analyze it, understand the faces of the stone, and then there is the option to now figure out where such a stone could fit in a stone wall. So it's something which a mason would do by hand, but on this scale, it's actually very handy that the robot can do this, and it was our PhD student, Ryan Luke Johns, who developed the algorithm for this fitting. You can see here the kind of the design cockpit of this machine. On the left, you see the design interface, where you see a selection of possible stones and the fit of the stones and proposals on where to put such a stone. And then basically there is a person here deciding, yes, I like this solution or not. On the right is the control of the robotic excavator. So this big machine here, you see there is no one sitting there. It's basically able to then pick and manipulate these stones autonomously without the driver. So this is kind of the Waymo of robotic construction. The robot control is done by a roboticist, from the group of Marco Hutter. So we are, of course, not developing this at this scale on our own. Just to also tell that there's a lot of collaborations involved in our projects. We try to work very interdisciplinary. We were then lucky to be able to build an 80-meter wall, which was composed out of natural stones and certain concrete demolition waste. Here again you see the driverless robot, and on the right you see the wall with certain leftover demolition parts as part of it. There's a spin-off founded, and it's part of our mission to also support young faculty and excellent researchers to bring their work into the world. And in this case, Brian Luke Jones is actually, who's originally an architect and studied here at Princeton, now is actually the CEO of this robotics company. So it's interesting what architects can all do in their life. Good, now let me shift a bit. So we are now with the materials. What can the materials do? How can we go towards the material in order to use computational design and digital fabrication to build more ecologically with these materials? But then there's another aspect. Will it all be built by robots? What about the humans? How could the human agency evolve with these digital technologies? And I would like to show this project because it was a weird story behind it, because I've shown you the winery Gantenbein, which we did in 2006. And here, 15 years later, we get this call from a Greek winemaker. And he said, "Oh, I really love your winery Gantenbein. We would like to have the same. We have this building, the raw structure, which is actually already built, and we would like to have basically such a facade. Could you also do this for us?" And we said, well, actually we don't like to repeat projects, and also it wouldn't make sense, it absolutely wouldn't make sense to now robotically fabricate brick elements, prefabricate brick elements in Switzerland and then ship them down to Greece in a totally different socioeconomic context to then install them there. So we said, we don't think we can do that, but maybe we have another way in which we could do that. And together with the researcher Daniela Mitterberger, we developed this project here. So you again see a large-scale facade application. It's 5 by 5 meters. Is one of these surface areas here with a bespoke pattern. Actually, here the bricks also have a differential a differential height in a mortar. How you say it? A mortar layer with a different height in between. And here it's built by the local craftsmen, and they were augmented by extended reality in a way where basically the craftsman could get the information on the digital fabrication from these systems. This was a very early prototype. By now we do this with the mobile phones. You see how this works. So here the craftsmen get the information. You see these red arrows on the screen where the craftsmen need to tap on the brick in order to get the position correctly. You see when the craftsman taps, these arrows get smaller, and like this basically they correct for all the position of the brick elements while building that. What was interesting for us to see is that these craftsmen didn't feel automated, so they didn't feel that they were taking away agency. Actually, they loved it. They really got into it. In the beginning, they were horrendously slow. I think it took them about an hour per brick. And then they got really fast, up to about 2-3 minutes a brick, which is reasonable, I think, for this complexity of the structure. And they really enjoyed it because, in a way, they became, almost like partners of the algorithm. They sometimes placed the brick exactly at the right position because they already knew, where this would need to go. They kind of learned the algorithm in some ways and became part of it. And we got really positive feedback by the craftsmen. This was, for me, the most astonishing part, because otherwise I would say, well, maybe the experiment would have failed, right? If you try to deliver digital information to craftsmen and they wouldn't like it, that would create a problem. But here, in that sense, they really felt augmented, and they found the job more interesting than just producing planar brickwork. Here's some architectural impressions. You can see how what kind of plasticity this wall unveils depending on the sunlight and the viewer position. Good. I'd like to show you this little project, which is a student project, which we just finished. It's the second last project which I'm going to show. And it also involves this augmented reality fabrication. So here you see the village of Disentis in Switzerland. And there's an interesting local community which is operating a kind of a church school there. And there was the remains of an old watchtower in the mountains there, which they wanted to revive and reenact. And they said, could you do something with us? They didn't have a lot of money, actually they had no money, but they had a lot of people that wanted to help in the village to realize such a structure. This was the structure the students designed for this very remote place. It's basically an 8-meter high tower with an internal circulation area, which you see here marked in orange, where you can actually walk inside of the structure, although you don't see this from the outside, that you can go into the structure. The students designed it in a kind of voxel system here marked on the left, but then they needed to think about modules which they could assemble, pre-assemble in our workshops, and then these modules would needed to be assemblable into larger so-called air modules, which could be flown to this site, because this is the only production method which would be reasonable and efficient there. Just to illustrate a bit of the process, the students first designed these systems which would find possible modules which could which they could aggregate together. Then these first designs, they looked very floor-like, which they didn't like, so they started to develop the algorithms further to actually start to kind of conceal the inner organization or free up the inner organization such that it became a very varied and complex object. Here you see then the organization of these modules. There's no module which is the same. They're all somewhat different in their inner configuration, but also their shapes are mostly different. And you can already imagine that it becomes a very, very dense experiential structure to see this from the outside, but also to be in it. Then these modules, they have a certain complexity. I won't go into details here, but basically we have multiple levels of slats, which are part of these volumetric modules. And the structure works in a way where basically we introduce more deviation from verticality in the main load-bearing columns towards the top. So the higher up you go, the more they start to kind of loosen up and go out of the vertical. And of course, we need the verticality to transfer all the loads. Then they devised how these modules will need to be transported, how they would need to be taken apart and reassembled after transport, such that they could go on site. And here's a virtual simulation of how these come together. And I think you can see already how nice these, spatial Tetrix parts actually work. So for me, it's also important to think a bit about architecture. How could we think more in chunks, rather than in pristine building parts. So these are really, it's an architecture made out of chunks which have their own inner logic, but are not traditional building elements which are easily recognizable as such. Then these were constructed in this kind of manual way. You see here on the left the construction supervisor with the mobile phone, so basically giving instruction to the person on the right where to put an element. Here another of these scenarios, and this little video exemplifies this. So basically we just bought this timber mill, which allowed us to produce these elements in-house. And then the robot here only had an assisting function, basically to hold this upper frame in the air. And here you see the app, which basically guided the students to put the right sled at the right location. And actually you wouldn't want to build this structure in any other way, because it's very hard to fit these elements in space in this complexity. Here's some test assembly. Then these were brought on site and were ready for the copter. Here then came the helicopter and started to lift these modules. It was actually very efficient. It took about 2 minutes to transport a module from the pickup place to the destination. Here we see the bird view. So this site is really on a ridge here. It's higher up from the street. This is how it looks from below. Incredibly precise. Very talented pilots. This is how it looks, how they basically received the element. You see how it just perfectly fits in place and needs to fit in place because there's not much time. It's a couple of people and hands, and this is how we assembled this entire structure. Really within, I think it was an hour or so. So this is how it all came together on the side, and here again an impression of how it looks inside. It's going to be up for about 5 years, so in case you come to Switzerland, please go and check it out. It's actually very nice, very solitude kind of place. Nice place to meditate a bit and be in the woods. Good. Last but not least, I would like to come to the topic of AI, because I hear it's everywhere here, and we also did a bit of our approach to it. We designed this structure, Semiramis. It's a 22-meter high structure for plants and animals only. So it's a structure which cannot be accessed by humans, with the idea that we look at these planters from the aspect of how much sunlight do they get, how much rain do they actually collect, and how big are they. The latter one is most important for the costs of this structure. So the client was most interested in the right ones. We were a bit more interested in the left ones. Then we basically created a generative system, which out of these parameters, which you see here on the left, basically created possible structures, which you can see on the right. So basically, these are combinations of what we call constellations. I'm going to show that in a second, with particular radii, which could be randomly selected in their size. So basically, we have chosen these 10 base constellations. These were basically base typologies which we were interested in, the ones which we thought are most interesting in terms of what they yield as architectural design. Then these base constellations, they could be spread in 115 different combinations on this available small triangular plot with the given structural elements. And then in combination with the different radii, which each of these, on each of the columns, that this gives an endless amount of possible design solutions. So we created 500,000 of these design solutions really randomly, in order to get a wealth of possible solutions. And the challenge here was, how can we actually reverse the design such that we can now, so let me go back, such that we can now actually say, okay, we would like to have more or less sun occlusion on these elements. We would like to have more or less rain occlusion on these elements. Give me a structure which fulfills these criteria. So actually reverse the design from our initial design parameters. So the system learned these structures and started to propose alternative structures which doesn't need to be part of this set, given these constraints. So what you see here is a little video. Here, for example, we changed the square meters from, I think, 300 to 100 square meters. And you see that immediately we get another design by the system. This really goes in real time. Or we change the rain occlusion to 10%, meaning that these planters should now be taken apart such that more rain falls onto these different planters. And we say, okay, this is nice, but a lot of column for very little vegetation surface, so we would like to go back to 300 square meters of surface. How would that look like? And we actually really started to design with this system, which we designed ourselves to design with. And actually, we were pleasantly surprised that it was fun to design this way. So we didn't feel that this artificial intelligence system was taking away agency, because we made it our system to design with, and we could interactively design with this system. And so finally we chose one particular structure, and we built it for the first time with 4 robots. So these are the 4 robots which we have available in our lab, and we used them to build a shell structure with these multi-layered timber plates. You see that here in simulation and here as a physical piece. So this enabled us, basically the robots were bringing the pieces at their exact location in space, then really driving them together at very good precision, such that we almost didn't need any form or false work to do this spatial assembly. Again, every plate is unique in its geometry, every position is unique. Then these plates were glued together. It's a startup project, a Swiss company that enables to glue such timber plates together in such a way that actually the structural forces can go fully through. Otherwise, you wouldn't want to do this with the normal timber structure. And this then creates this structural shell. Again, very thin, 8 centimeters thick. Finally, here there's some silicone protection of the glue on the outside. Again, there is, if I talk of robotic fabrication, it's not only robots. Usually there's many more humans than robots involved with robotic fabrication. It's really this hybrid reality of producing with digital means and physical human production and thoughts. And here's the final structure. And slowly the vegetation starts to take over. The landscape architecture project, or the plantation, is done in such a way that it's 100 local species from the local environment there. And they basically are curated to grow in a quite an uncontrolled way. They're only cut back, I think, once a year. Otherwise, basically, it's a new urban wilderness which is being created. With this, I'm at the end of my lecture. Thank you for your attention.